Welcome to lecture number 28. We are studying circuit analysis. Today we will study Norton's theorem for AC circuits. Before that, we have studied in our earlier basic electrical engineering BEE lectures the same Norton's theorem for DC circuits. To apply Norton's theorem, it's a sister to the Thevenin's theorem we studied earlier, and the steps to perform Norton's to apply Norton's theorem to find an unknown quantity are the same as we studied for DC circuits. The video of applying Norton's theorem on DC circuits is available on my YouTube channel. Today we'll revise the steps and then we'll apply Norton's theorem on this example circuit. The first step is the same as it is for Thevenin's theorem. We'll remove load resistor, then we'll find ISC. ISC is I short circuit. We'll replace ZL with a short circuit and we'll find the current flowing through that path. And then we'll replace sources with their equivalent impedances. Voltage sources will be replaced with short circuits and current sources with open circuit, and we find Z Thevenin, and then we'll draw an equivalent circuit having this ISC in parallel with Z Thevenin in parallel with the ZL that we removed in step number 1. Right, let's start solving this example. Here we have this circuit. We have already solved this circuit for this unknown quantity V out using Thevenin's theorem. Today we'll solve it using Norton's theorem and we'll reach to the same answer. Right. The first step is that we should remove ZL. This is the load resistor ZL because we have to find voltage drop across it. So in step number 1, we have to remove it and we'll replace it with a short circuit. We'll find the current through this short circuit as step number 2. To find this ISC short circuit current, we can either apply nodal analysis, we have to write one equation for that, and then or we can apply loop analysis. Let's apply loop analysis, assuming this to be loop number 1. This is current source, We'll apply loop analysis. We'll assume this as current as the first loop. This loop cannot be assumed to be loop number 2. We have studied this fact using in our earlier lectures when we applied loop analysis for DC circuits. You can find that video in my YouTube channel. We cannot consider this as a loop because in that way this current source will be shared among these two loops. So we have to find a loop that bypasses this current source. So when we face this situation, we go for a longer loop or for a bigger loop, and we'll ensure that this loop bypasses this current source so that it is not shared between our two assumed loops. So for loop number 1, I1 is minus 2 at an angle of 90 degrees. Why 2? Because our assumed direction of current is opposite to the direction of this current source. This is our equation number 1. Alright, equation number 2, we'll write equation for this loop number 2. Loop number two, right? In this loop, we have this source where the presumed current enters from the negative side of the source. This means it's a voltage rise. We'll write it as negative. Plus, through this 2 ohm resistor, there are two currents. I1 flowing rightwards, I2 flowing rightwards. So we have two currents flowing through this 2 ohm resistor. Then comes this minus J2 ohms Z ZC, the capacitive reactance, minus J2. We have only one current I2 flowing through it because I1 has this path. So through this 2 ohm resistor, we have two currents flowing in the same direction. Therefore, we have written I1 plus I2. And through this minus J2 ohm capacitive reactance, we have only I2 flowing through it. Now we have two equations and two variables. We can plug the value of I1 here. In that case, we'll have only one equation and only one variable I2. In my notes, I have solved it. I have gone through all the mathematics for you and reached to the answer I2. There are some steps which I am omitting here, but they are there in my notes. Plugging the value of I1 in here and then solving for I2 gives us I2 is 8.6 at an angle of 54.4 degrees. Right. Since this I2 is the same as ISC, so we have gone through step number 2 and now we have to, this I2 can also be written as ISC because these two currents are the same. Then we have to go through step number 3 to find Z Thevenin. Finding Z Thevenin is the same as we did for Thevenin's theorem. So Z Thevenin for Thevenin's theorem and Norton's theorem is the same. To find Z Thevenin here across open ends, we have to replace sources with their equivalent impedances. This has infinite impedance, replace it with an open circuit. This has a zero impedance, replace it with a short circuit. So this J2 ohm is not in the circuit because one end is hanging in the air. So we have these two components in the path. So Z Thevenin is the same as we computed in our last lecture. This is 2 minus J2 ohms. Now we have Z Thevenin, we have ISC. Now we are ready to perform step number 4, which is we draw an equivalent having this current source ISC, that is 8.6 at an angle of 54.46 degrees in parallel with Z Thevenin, which is 2 minus J2 ohms. And then we'll put the ZL that we removed in step number 1. It was 2 ohms. And we'll find voltage drop across it. Right. To find voltage drop across this 2 ohm resistor, we have to first find the current flowing through it. So we'll apply current divider's rule and let's call it I out. I out is the other impedance in numerator, the sum of the two in denominator times the total current entering 54.46. So solving this gives us I naught is equal to 5.43. I'm omitting some mathematics here, but it is there in my notes. 5.43 at an angle of 36 degrees. Finding B out now is simple. Let's apply Ohm's law. B out is I naught times 2 ohms. Centimeters. So V out is I naught. This times 2 gives us YQ equal to 10.9 at an angle of 36 degrees. So this is the same answer we computed when we applied Thevenin's theorem on this circuit in our last lecture. We'll continue dealing with AC circuits in our upcoming lecture.